Hi kids, I realized there's going to be a pretty good amount of time between our review day and the actual day of the test, so I thought I would go ahead and make a video for these review problems just to give you an extra opportunity to review. Alright, so let's go ahead and start with the first one. So we got some information about methanol here. It tells us that the enthalpy of combustion can be determined either theoretically or experimentally. It gives us the equation. Says use the information in table 11 to determine the theoretical enthalpy of combustion of methanol. So remember, we have a number of mathematical tools we're going to be using in this unit. It told us to go to table 11. If you're unsure of which tool to use, turn to table 11. You'll see that it's bond enthalpies. So when we're doing calculations with bond enthalpies, delta H for the reaction will be calculated using the sum of the enthalpy used to break all the bonds, so bonds broken minus the sum of all the bonds formed. So of course, in a chemical reaction, the bonds and the reactants are broken and then they're reformed to make products. So this is essentially reactants minus products. All right, so first thing I'm going to do is figure out which bonds are going to be broken. Now, it may be helpful for you guys to draw these structures because then you can visually see the bonds, but in the interest of time, I'm just going to say what they are. So the first thing I see in methanol is I'm going to have 3 bonds that are carbon to hydrogen. I'll have 1 that is carbon to oxygen and 1 that is oxygen to hydrogen. That takes care of methanol. Now we have 1.5 moles of oxygen. You got to remember that the oxygen molecule is double bonded together. Since we have 1.5 moles, I'm going to have to multiply the value of that bond enthalpy by 1.5. So we're going to have 1.5 moles of those oxygen-oxygen double bonds. In our products, we have carbon dioxide. From carbon dioxide, you're going to have 2 carbon-oxygen double bonds. To that, we're going to add the bond enthalpy for 4 oxygen-hydrogen bonds, because of course each water molecule has 2 oxygen-hydrogen bonds, so 2 moles of them would have 4 moles. All right, now all we have to do is substitute the values from the data booklet. So I'm not going to show you the data booklet. You can look at it yourself if you need to. So I'm going to do 3 times the carbon-hydrogen bond enthalpy, which is 414, plus the carbon-oxygen, which is 358, plus the oxygen-hydrogen, which is 463, plus 1.5 times the oxygen double bond, which is 498. And then I'm going to subtract away 2 times the carbon-oxygen double bond, which is 804, plus 4 times the oxygen-hydrogen, which of course from the previous factor is 463. Now all you have to do is punch the numbers into your calculator, and in this case I'm just using the key for the final answers just again to save some time. You should get negative 650 kilojoules per mole. I'm going to switch marker here to a marker that's a little bit fresher and newer. Alright, so part B says the enthalpy of combustion of methanol can also be determined experimentally. It tells us that we got a burner filled with methanol. It was weighed and used to heat water in a test tube as illustrated below. And if we look below here, we have some data showing us what was collected. So I have the initial and final mass of the burner and methanol. So that can give us the mass of methanol if we get the difference between those. I'm given a mass of water and an initial and a final temperature for water. First thing it asks us to do is calculate the amount in moles of methanol burned. So this one's really more unit 1. All we got to do is calculate the number of moles of methanol. I know from the data the number of grams, so we just have to convert from grams to moles. So we have 80.557 grams to begin. I'm going to subtract away 80.034 grams, and that's going to give me a total mass of 0.523 grams. To convert that into moles, we divide by the molar mass of methanol, which is 32.05 grams. When you do that, you're going to get 0.0 0.0163 moles. Piece of cake. All right, next it says calculate the heat absorbed in kilojoules, pay attention to your units, by the water. So we're going to be using Q equals mc delta T here. I know that because I have a change in temperature. Now, it's really important that you understand which mass we're going to be plugging into this equation. Our temperature, the thing that's having its temperature changed is water. We're going to be using the specific heat of water. That means that the mass we plug in needs to be the mass of a water. So let's go ahead and plug our values in. So we have a mass of 20.000 grams of water times the specific heat, which is 4.18, times the change in temperature, final minus initial, so 26.4 minus 21.5. I get that Q here is, I'm just looking at the key again, 410 joules. Now we have to be careful here because when we're plugging in our values, we have to know what the output or the unit of our answer is going to be. So really quickly, just over here, when we plug the values in, if we plug in our mass in grams, specific heat is joules per gram degree Celsius, and delta T in this case is degrees Celsius. When we cancel all the units out, we're left with joules. That's how I knew that my unit was joules here. Since we're asked for kilojoules, we have to divide this value by 1,000 to make the conversion, and that will be 0.410 kilojoules. Hey. All right, moving right along. Continuing with the same problem, it now says, come on, you gotta be able to see that. There we go. Determine the enthalpy change in kilojoules per mole for the combustion of 1 mole of methanol. So this is just the next part of the problem. This is a long multi-step problem, as you can see. Well, when we're calculating delta H, it's going to be the negative Q value divided by the number of moles of the limiting reactant. So we actually calculated Q and N in the previous part of the problem. So Q was 0.410 kilojoules. Don't forget to negate it. The number of moles was 0.0163. When you run this through your calculator, you're going to get negative 25.0 kilojoules per mole. Next, we're still in the same problem. It says the data booklet value for the enthalpy of combustion for methanol is negative 726. Suggest why this value differs from the values calculated in part A and B. So now we got to remember our discrepancies. So part A was using bond enthalpy. So of course, when we're using bond enthalpy, the values are averages, so they're not particularly too accurate. And of course, in part B, we're doing the experimental. Now the assumption we make here is as this burner burns, all the heat from the flame goes into the test tube. But of course, the heat goes out in all directions, so only a portion of it goes into the test tube. So we know that our value is going to be a little bit lower than it should be. So you could say not all heat was absorbed by the water. All right, moving right along. We got propene can be hydrogenated in the presence of a nickel catalyst to form propane. Use the data below to answer the question that follows. So it's really important that you analyze the data. When you look here, we see these are enthalpies of formation. That's what that F means. Whenever we're doing enthalpy of formation, it's going to be the delta H value is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So the first question here says, outline why the value for the standard enthalpy change of formation of hydrogen is 0. Remember, elements will always have a value for enthalpy of formation of 0 because they were already formed before we got here. They were born in the hearts of stars. So elements have no value for enthalpy of formation, or something along those lines. So So it says calculate the standard enthalpy change for the hydrogenation of propene. This is just the reaction. Remember from Unit 3, we're going to take propene, add it to hydrogen, and produce propane. So if we're doing delta H is the sum of the delta H values of the products minus the sum of the delta H values of the reactants, we know that propane is our product. Here's delta H, so it's going to be negative 104. If you actually write out this equation and balance it, you would see that everything is 1 to 1. This is an addition reaction, so we don't have to worry about any coefficients. From that, we're going to subtract away the enthalpy of formation of propene, which is 20. Hold on a second. Yes, because that's the reactant, sorry. 20.4, and we get this enthalpy of the enthalpy of this reaction, excuse me, is negative 124.4. I don't know why I don't trust my math here. I mean, it's pretty standard. Okay, and that'll be kilojoules per mole. All right, moving along, it says calculate the standard entropy change. Now, if it's entropy of formation, then it's the same equation, only we're going to switch the H's for S's. So delta S here will be the standard entropy of our product, which is propane, so 270, minus the sum of the entropy of hydrogen, 267, and propene, or no, excuse me, hydrogen is 131, that was propene. All right, when you punch the numbers into your calculator, you get negative 128 joules per mole Kelvin. Remember, entropy will have a unit of joules, so we're going to have to change that. And it says, determine the value for delta G for the hydrogenation of propene at 298, piece of cake. Delta G, we have our equation is equal to delta H minus T delta S. It's got to plug in the values that I calculated up here. So delta H was negative 124 minus the temperature, which is 298, times the entropy change, which is negative 128, but remember that's in joules, so we have to divide that factor by 1,000. When we plug the values into our calculator, we get the standard Gibbs free energy is negative 86.3 kilojoules per mole. All right, last bit of this problem, it's at 298 Kelvin. The hydrogenation of propene is spontaneous, and that makes sense because our delta G value here is negative. Determine the temperature above which propane will spontaneously decompose into propene and hydrogen. So it wants to know when this reaction is going to go from spontaneous to non-spontaneous. And since a positive value for delta G means non-spontaneous and a negative value means spontaneous, we essentially just have to set delta G equal to 0. So 0 will be equal to hold on, let me write out the equation again. It's early in the morning. I'm not quite here yet mentally. All right, so we're going to set delta G to 0. Delta H is negative 124.4 minus 200, or minus the temperature, which is going to be our variable, so we'll call that X. I'm sorry, things are all falling apart here. Times negative 0.128. Don't forget to carry through the unit. Sorry, I don't know why I'm freaking out here. And when you solve for this equation, you're going to get that the temperature is equal to 972 Kelvin. Pretty high temperature. All right, next problem. Two students were asked to use information from the data booklet to calculate a value for the enthalpy of hydrogenation of ethene to form ethane. Here's another addition reaction. John used average bond enthalpy. Merritt used the values of enthalpy of combustion from table 13. All right, so I'm going to, for part A, since John used average bond enthalpies, we've already done an example of one of those problems. So I'm just going to go ahead and give you the answer for that problem, as opposed to working the whole thing out again. and John got via the bond enthalpy method that the enthalpy change for this reaction was negative 124 kilojoules per mole. If you want to know how to do that one, just go back to the beginning of the video and see how we did the other bond enthalpy calculation. So part B says determine the value for the enthalpy using the values for enthalpies of combustion given in table 13. So if you're asked to use table 13, that's most likely going to be our energy cycle. So we have our equation up here. It wants to know the enthalpy for this reaction. So let's go ahead and rewrite the reaction here to make the cycle. C2H4 plus H2 makes C2H6. So we're going to combust ethene to make carbon dioxide and water. Of course, we have 2 moles of carbon here, so we're going to make 2 moles of carbon dioxide and 2 moles of water here. When we combust ethane, we're going to make those things plus another mole of water. So we have our processes here. This arrow represents the enthalpy of combustion for ethene, this one for hydrogen, and this one for ethane. The arrow here just represents the enthalpy change of the reaction. So now we just got to sub the values for the enthalpy of combustion for each of those reactants and products. I'm not going to bother showing you the data booklet, it's too much of a pain, and we'll solve. So we're going to calculate this arrow, so we're going to travel around the cycle to the front of the arrow, adding or subtracting all the values for the arrows as we encounter them. So if we're going with the arrow, you add. If we're going against the arrow, you subtract. So for ethene, here's ethane. Let me underline it just so I can come back to it. Interesting. I don't see ethene in here. I'm going to pause the video and just look up a value. Never mind, it's there. I just couldn't find it. All right, so ethene is negative 1411 plus our enthalpy of combustion for hydrogen, which is negative 286, minus the value for this, because we're going against the arrow, and ethane is negative 1561. When you punch all the numbers into your calculator, you're going to get negative 136 kilojoules per mole. So our values are pretty close here. Pretty close, but not exactly the same. Suggests one reason why John's answer is less accurate than Merritt's. Well, because John used average bond enthalpies, and average bond enthalpies are, like the title says, averages. And so the values are not necessarily very accurate. All right, going down some more here. It says John, and then it asks us to calculate the percent difference. All right, so to do that, we just have to subtract the values. 136 minus 124 and divide by one of them, either 136 or 124. I'll divide by 136. And I got 8.82%. All right, so again here it's asking us to do an average bond enthalpy calculation. Just in the interest of keeping this video as short as possible, I'm just going to go ahead and give you the answer here as well. And for this, John also got 124 kilojoules per mole. Excuse me. It says the percentage difference between these two methods, average bond enthalpies and enthalpy of combustion, is greater for cyclohexane than it was for ethene. John's hypothesis was that it would be the same. Determine why the use of average bond enthalpies is less accurate for cyclohexane, question shown above, than it was for ethane. Deduce what extra information is needed to provide a more accurate answer. All right, so one thing we have to remember is that bond enthalpies are only usable if everything is in the gaseous phase. And in the reaction, sorry, I'm looking at the wrong reaction. The reaction with cyclohexane and cyclohexene, these are both liquids. and so the values will be off even more. All right, last page. Standard enthalpy change of 3 combustion reactions is given below. Based on the information, calculate the standard enthalpy for the following reaction. So whenever we are given, a series of equations and an overall equation, it's going to be Hess's law. I like to label each reaction A, B, and C, and then set up a little equation to calculate delta H. So again, here we're going to be looking for our reactants in the overall reaction and finding them in our steps and manipulating the step to make it match. Whatever manipulation you have to do to the step, you also have to do to the delta H value. So the first reactant I have here is ethane. I see in my overall equation, ethane is on the reactant side and it has a coefficient of 1. I find ethane in step 1. It's on the reactant side, but it has a coefficient of 2, so I have to take the value for A and cut it in half. Next reactant I have is ethene. I find ethene in step C. Now in my overall, ethene is on the product side and it has a coefficient of 1. In our reaction, it has a coefficient of 1, but it's on the wrong side. So I have to reverse that reaction. If I reverse the reaction, I reverse the sign of delta H. So to 1/2 A, I'm going to add negative C, whatever the negative value for C would be. Finally, we have hydrogen. I find hydrogen only in step B, reaction B. I have it here on the product side with a coefficient of 1. Here it's on the reactant side with a coefficient of 2. So not only do I have to flip it, but I also have to multiply it by 1/2. So we're going to add negative 1/2 times the value for B. Once you have your little equation set up, all you got to do is substitute in the values. So we're going to take 1/2 the value of A, which is negative 3120. To that we're going to add the negative value of C, which is negative 1411, so we're going to add positive 1411. And to that we're going to add 1/2 times the negated value for B, which is negative 572, so it'll be 1/2 times 572. Punch the numbers into your calculator, and you should get 137 kilojoules per mole. I'm making a video. Let me pause it and I'll see. All right, let's go ahead and wrap this up. All right, here we have a Bohr-Haber cycle. You may recognize this from Lab 5.3. It says the magnitude for each enthalpy change, A to E, are given in kilojoules per mole, but their signs, plus or minus, have been omitted. This is because you have to have an understanding of how the cycle works. Let's just go ahead and look at the cycle. We have potassium solid going to potassium gas. That will be the enthalpy of atomization, positive. Here we have calcium gas going to gaseous calcium ions. That is the ionization energy, so we know that that will also be positive. Here we have 1/2 mole of bromine molecules being turned into bromine gas. Oh, look at that. That is step C will be the bond enthalpy plus the enthalpy of vaporization, because we're going from liquid to gas, but both of those values are probably combined right in there. And then from bromine gas to bromide ions, that will be the electron affinity, which of course has a negative value. The gaseous ions being connected to the solid product is lattice enthalpy, but typically the arrow goes from the solid to the gaseous ions, and it has a positive value. So since this arrow is going in the opposite direction, 670 here will have a negative value. So it says state the names for the enthalpy changes C and D. So C, of course, is bond enthalpy, like I mentioned. Something tells me, let me look at the key here, something tells me you could also say enthalpy of vaporization, because we are going from liquid to gas. I'm recording a video, Leah. I'm almost done. Can you just let me finish? Thank you. And then D, where's D? Right here is electron affinity. I'm rushing now. All right, to do switch 2 enthalpy changes have negative signs. So as we mentioned, bond enthalpy, or I mean electron affinity, and in this case lattice enthalpy because it's the reverse lattice enthalpy. Determine the value for the enthalpy of formation. Enthalpy of formation is this arrow up here. If we're going to calculate that arrow, we're going to travel around the cycle from the back of the arrow to the front, adding or subtracting all the values as we encounter them. So we're going with all of those arrows. So the first thing I'm going to do is take 90.0 and add 418. To that I'm going to add 112, and then I'm going to add negative 342. Don't forget to carry the sign through. Now I come around, I'm going with this arrow, so I'm going to add negative 670, punch in all the values, and you should get negative 392 kilojoules per mole. And finally it says explain why the quantitative value for the lattice enthalpy of calcium bromide is larger than the value for the lattice enthalpy of potassium bromide. All right, so remember the two things that affect lattice enthalpy are the size of the ion, the amount of shielding in it, and its oxidation state, because a greater charge would mean a greater attraction between the ions, which would mean it would be harder to separate them. And if the ions are larger, they have more shielding, which would decrease the attraction, which would lower the lattice enthalpy. So, of course, calcium has an oxidation state of 2+, potassium has an oxidation state of 1+. Calcium and potassium, calcium is actually a smaller ion as well, so you'd expect the lattice enthalpy of calcium bromide to be larger for those reasons. All right, kids, hopefully this helps. It was a little bit sloppy, I know, but I didn't do a plan beforehand, and it's early in the morning. So hopefully you can use this to study, and I'll see you on test day.